Hello and welcome back to Patch Math, where today we are going to apply what we learned in the last video to trig inverses. So I had started a video intending to talk about trig inverses, and then when I was explaining the unit circle so that we can understand these things correctly, I went off on a tangent, no pun intended, and went into interpreting what trig functions look like, or what trig, I got tongue-tied there. What these trig functions look like on the unit circle without the inverses. So I was just testing the angle 30 degrees or pi over 6 in terms of sine, cosine, and tangent, and how that would look on the unit circle, where x is cosine, y is sine, and y over x is your tangent. With that being said, how does basic trig identities apply to trig inverses? Now, I love to teach my students about where the domain and ranges for trig inverses come from. Because if you look at the domain and range of the regular trig functions, you'll notice it's not a direct flip. All right, that's super important. Now, you'll see that the range, like on sine, basic sine function, doesn't go higher, range, output, up and down, doesn't go lower than -1, doesn't go higher than 1. So when we flip, that does become our domain. However, once our domain for our trig inverse is restricted between -1 and 1, that is going to change the outputs that we're able to have. Because if you think about in regular sine function, our domain for a regular sine function is all real numbers. We can plug everything into a regular sine function. However, if we do that domain range flip-flop like we do for a lot of trig functions, you'll notice this isn't a direct flip-flop. Our range for sine is not all real numbers. And that's because when your domain gets restricted like this, it's going to restrict your outputs. Why is this important? Well, when we are doing these problems, sometimes some resources like to throw in problems in which you're given something in your trig inverse that is not allowed in that domain. So in other words, anything if we're talking about sine, anything outside of -1 and 1 for x, we can't do. If they asked us to plug in 2 there, that would be undefined, and that's so important. I see a lot of students skip over this check because when you start applying this in different situations, the resources don't give you those weird ones anymore. However, when you get to the SAT or the ACT or one of those standardized exams, they like to give you the weird ones where you got to remember that step that you frequently skip over. The very first thing that we need to do is to check to make sure that what we are given here is allowed in our domain. So I'm not going to do all of these problems, but I am going to go ahead and talk about the domain of all these problems really quickly for sine. So I just highlighted what they're asking us to input. So we got to make sure that input is allowed in this domain over here for sine inverse. Well, lucky for us, square roots of 2 over 2 is between -1 and 1, so we're good. Looking at square roots of 3 over 2 for number 2, this one. Looking at that is also between -1 and 1, we're good. -1/2, looking at that's also between -1 and 1, we're good. Negative square roots of 2 over 2, that's also between -1 and 1, we're good. So all of these can be done. However, some resources aren't so kind, and they might ask you for sine inverse, super important. Sine inverse of, and they usually write it in a way that's difficult to see. But let's go ahead and just look at an outlier that we can see cleanly in our head. 2. We look, can we plug 2 into the domain? Where is 2 in the domain for sine inverse? No, it's not. It's greater than 1. It's not in our domain. The solution to this one is undefined. I want to go ahead and start the special case because this resource skips over it. That is undefined. That being said, let's just focus on number 1. We already got the first step, so I'm going to write our list of steps here. All right, so is the input given in our inverses domain? So in this case, looking at number 1, I'm going to go ahead and copy it on down. Now, in that video in which I went off on a tangent of basic sine function or basic trig functions, the reason I did that is because I have trouble visualizing these things in reverse in my head. I actually like to go ahead and write this down. Whenever you are dealing with regular trig, you plug in a theta. You noticed that in our last video. You plug in a theta and you output a side length or ratio of side lengths, depending on if you're dealing with tangent. In this situation, the input is no longer theta. The input is the side length or ratio of side lengths. So that is super important. This is not theta. We are finding theta. We are finding the angle that would input that. Now, why am I going to go ahead and write this equal to theta? We're finding theta. So I can come in here. If we're going to undo a trig function, as an inverse trig function, its inverse is the regular trig function. So I'm going to come in here and I'm going to take the sine of each side, because when we are solving equations, what we do to one side of the equation, we must do the exact same thing to the other side of the equation. That is super important. And so once I can get that one cropped off here, there we go. All right, you're going to see me come in here with this sine. It's sine of this whole thing. Sine of this. That whole thing there. And I'm going to move my theta over because what we do to one side, we have to do the exact same thing to the other. So we have to take the sine of this entire side too. Sine of theta. Well, why is it important we write it this way? Sine of sine inverse, that cancels. Now we know we have square roots of 2 over 2 is equal to sine of theta. That seems familiar, doesn't it? Let's go ahead and connect back to what we learned in the last video. So sine of theta. So you're like, oh, I'm solving for this thing that's on the inside of my sine though, but that's how we think on the unit circle. We have to be careful. We got to remember, we started with inverses. So here, the unit circle gives us a lot of outputs for sine, but not all of those all of those thetas can be outputs for sine inverse. Why? The range restricts us. We are restricted between negative pi over 2 and pi over 2 with the range. Super important here. On the unit circle, if we were being restricted between negative pi over 2, if you watch my video about coterminal angles, you will know that negative pi over 2 on the unit circle is the same thing as 3 pi over 2. And we start at negative 3 pi over 2 as our range, our outputs here. Because remember, theta is your output on your sine, or on your trig inverses, like sine inverse. And we go all the way to pi over 2. Why is this important? Well, that tells us that anything outside of that arc, those are not solutions. When we're thinking about the remember, sine is y, all right? Sine is y. The y that is square root of 2 over 2 on the unit circle, you'll see that we get that in a variety of places. So we got square roots of 2 over 2 here as our y on our unit circle, and we have the negative versions of it in the bottom two quadrants here, and we don't care about the negative versions, so I'm going to skip over those. Well, why is this important? Notice we have two potential solutions here. Either pi over 4 or 3 pi over 4. However, we don't actually have two solutions here because we started with an inverse. The output for sine inverse can only be between negative pi over 2 and pi over 2. Therefore, anything outside of the quadrant 1 and quadrant 4 we cannot use. That means we cannot use quadrant 2, and quadrant 3 didn't matter anyways because there wasn't a solution in it, but we can't use those for sine inverse. Well, that leaves us with one solution. So in this case, we are theta. That's what we were solving for. I just wrote it in this alternate form so I could think about the input that gives me that output. So we can find that output on the unit circle within the restrictions of the inverse and find what the input was that went with it. We're working backwards. So our theta here is the theta that goes with the square roots of 2 over 2 in the y coordinate. That's pi over 4 in radians or 45 degrees. And I am going to use radians because that's what we we use that a lot more in a lot of our math classes like pre-cal. So pi over 4. There you go. And that is how you find sine inverse. of square root of 2 over 2 using domain and range and your unit circle. I am going to go into a couple more examples in the following video or videos. So for now, thank you so much for your time.